Hello students, welcome to EPG Pathshala. I am Dr. Shilpa S. Sapadgaonkar from Manavrachna International University. Today, we are going to discuss about a module, Supercritical Chromatography, Introduction and Principles under paper Chromatographic Techniques 2. The objectives of this module are to understand formation of supercritical phase, to understand the theoretical principles of supercritical fluid chromatography, to know the advantage of supercritical fluid chromatography, that is SFC, over gas chromatography, GC, and high pressure liquid chromatography, that is HPLC, to know about different types of mobile phases used in supercritical fluid chromatography, to know about the effects of modifiers and additives in supercritical fluid chromatography. Supercritical chromatography is an evolving separation technique. One of the most important challenges faced by the analytical chemists today is the separation of complex mixtures. Separation is the key to determine identity and purity of a compound, and there is always a need of fast and efficient techniques of separation and analysis. Supercritical chromatography is one of these. Supercritical fluid chromatography uses supercritical fluids as the mobile phase. Usually, carbon dioxide is used as mobile phase because supercritical stage in carbon dioxide is achieved at comparatively mild temperatures and pressures. The supercritical fluids have properties that are intermediate between gas and liquid, and hence supercritical fluid chromatography can combine the beneficial features of HPLC and GC. The first use of supercritical fluid as mobile phase was described by Klesper and Turner in 1962. However, the technique did not gain much importance till 1982 when first commercial instrument for supercritical chromatography was introduced by Hewlett-Packard. Advancement in instrumentation continued thereafter. New applications were explored in 1980s. In 1986, Lee Scientific developed capillary columns for supercritical fluid chromatography. Further innovations in instrumentation were carried out during the following years. In 1982, Hewlett-Packard introduced second instrument for SFC. With the continued efforts of scientific community, SFC today is an established technique for many different types of applications. It has been employed in the separation of numerous compounds encompassing polycyclic aromatic hydrocarbons, petroleum products, polymers, food products, cosmetics, and pharmaceuticals. To understand the formation of a supercritical phase, we will consider a phase diagram of a substance. Phase diagram is a graphical representation of physical states of a substance under different conditions of temperature and pressure. Pressure is represented on the y-axis in the graph and temperature is represented on the x-axis. The points on the curve represent the equilibrium conditions where two different states coexist. As the temperature increases, the substance changes from solid to liquid and from liquid to gas. In the phase diagram, you can see a point demarcated as a triple point. Triple point represents the conditions where three different phases are in equilibrium with each other. In the phase diagram, you can also see a point which is denoted as critical point. Critical point is the point at which the substance is at critical temperature and pressure. Critical temperature is the temperature above which a gas cannot be liquefied regardless of the pressure applied. Critical pressure, it is the pressure required to liquefy a gas at its critical temperature. Substances, when subjected to temperature and pressure above the critical point, attain supercritical state where distinct liquid and gas states do not exist. Table 1 compares the properties of gases, liquids, and supercritical fluids. We can see that supercritical fluids have properties that are intermediate between gas and liquid. Characteristic density of a supercritical fluid is between a gas and a liquid, and it is closer to liquid. Since supercritical fluids have a higher density than gases, they are better solvents. Diffusivity of a supercritical fluid can be 100 times more than that of liquid, but 1000 to 10,000 times less than a gas. Viscosity of a supercritical fluid is similar to gas and 10 times less than liquid. Thus, supercritical fluids show lower resistance to mass transfer of the components that are flowing through them. When the sample is introduced in a chromatographic column, it is injected as a narrow band of equilibration. During the flow of the analyte along with the mobile phase, the band broadening occurs due to many reasons such as non-uniform packing of the stationary phase, diffusion, and limitations to mass transfer. The efficiency of any separation in column chromatography is described by HETP, or height equivalent to theoretical plate. The column is divided into a number of adjacent imaginary segments known as theoretical plates. The height of this equilibration band is also known as the theoretical plate, or HETP, of the chromatographic column. Complete equilibration of analyte between the stationary and the mobile phase occurs within each theoretical plate. The column is divided into a number of adjacent imaginary segments called theoretical plates. The efficiency of any separation in the column chromatography is described by HETP, or height equivalent to the theoretical plate. Greater separation occurs with greater number of theoretical plates, that is N, as the plate height, or H or HETP, becomes smaller. The total number of theoretical plates in a column is given by following equation: H is equal to L by N, where N is the number of theoretical plates, L is the length of chromatographic column, H is the theoretical plate height. The Van Deemter equation relates the HETP with properties of mobile phase, stationary phase, and that of analyte in a chromatographic column. Van Deemter equation is given by H is equal to A plus B by V plus C by V. Here, V is the velocity of the mobile phase. The term A is related to eddy diffusion. The term B is related to the longitudinal diffusion of the analyte while flowing through the column, and the term C is related to the mass transfer limitation in mobile phase and the stationary phase. The term A in the above equation is independent of the flow velocity and dependent on eddy diffusion. Eddy diffusion takes place due to small differences in the particle size of the packaging material or its differences in packing uniformity. Since gas chromatography, or GC, is operated in open columns, A term is negligible in GC. The term B is related to diffusion of the analyte. Band broadening occurs when analyte molecules follow different alternative path lengths while flowing through the column. Since the diffusivity is limited in liquid, the B term in Van Deemter equation can be considered negligible in HPLC. The term C appears due to resistance to mass transfer of the solute between the stationary and mobile phase. The Van Deemter plot. Figure 2 is a typical Van Deemter plot which gives a graphical representation of changes in the three terms A, B, and C in the Van Deemter equation with respect to average linear velocity of the mobile phase. It can be seen from the graph that the term A, or eddy diffusion, does not vary a lot with flow velocity. The term B is contributed by the longitudinal diffusion of the analyte due to the concentration gradients existing in the column. This term is quite high at low mobile phase velocities. Therefore, use of high mobile phase velocity, shorter and narrower columns reduces this term in the equation. The term C signifies the resistance to mass transfer encountered in the column for transfer of analyte between the stationary and mobile phase. The sum of all these terms determines the HETP in the column. At optimum operating conditions of a column, as given in the diagram, the HETP is at its minimum, that is, the column is operating at its maximum efficiency. Now, figure 3a shows a typical Van Deemter plots obtained for analyte flowing through HPLC or supercritical fluid chromatography column. It can be seen that SFC can be operated at 4 times greater flow velocities as compared to HPLC without appreciable increase in plate height. Supercritical fluids have lower densities and viscosities than liquids. This facilitates the diffusion of solutes, and therefore solutes have large diffusion coefficients in the supercritical fluids. Therefore, SFC has a greater efficiency at high linear velocity as compared to HPLC. In the slide, you can also see a comparison between the retention times obtained in HPLC and SFC. It can be seen that SFC has far less retention time as compared to HPLC. That means it substantially reduces the analysis time. Supercritical fluids have higher diffusivity and lower resistance to flow. The pressure drop in SFC is about 1/3 to 1/5 of the pressure drop in HPLC, even at 3 to 4 times of higher flow rates. This avoids costly high pressure pump requirement in SFC. Supercritical chromatography is gaining importance due to its numerous advantages such as 1. High speed analysis. Low viscosity and higher diffusion coefficients of the supercritical fluids allow quick and efficient separation. Low pressure drop across the column. High diffusion coefficients and low viscosity of supercritical fluids result in lower problems due to pressure drop across the columns. Third, ability to analyze a wide variety of analytes. SFC can be applied to analyze many solutes without any derivatization. Analysis of thermolabile compounds. Due to low operating temperatures as compared to gas chromatography, SFC can be applied to thermolabile compounds also. It uses eco-friendly mobile phase. It offers a wider choice of detectors as compared to HPLC. In the present slide, the important advantages of supercritical fluid chromatography over HPLC are given. Supercritical fluids have low viscosities than the liquid. Therefore, this results in faster analysis, less pressure drop across the column. Use of open tubular column is feasible here. The column lengths become shorter. We have a wider choice of detectors, and the resolution power of SFC is much higher than HPLC. Advantages of supercritical fluid chromatography over gas chromatography. Analysis of non-volatile, polar or adsorptive solutes is possible in SFC without derivatization. Analysis of thermally labile compound are also possible here, but in GC it is not possible. Low density of mobile phase in gas chromatography limits the molecular weight of compounds that can be analyzed by GC. SFC can be employed for analysis of high molecular weight compounds. Table 2 lists some of the possible choices of supercritical fluids that can be used as mobile phase in supercritical fluid chromatography. From the table, it can be seen that critical point for carbon dioxide can be reached at mild temperatures and pressure, that is 72 atmosphere pressure and 31 degrees Celsius. These are practically attainable in equipment. Moreover, other qualities of carbon dioxide, such as its inert and non-toxic nature, good solubility for non-polar substances, makes it a popular choice as a supercritical chromatography mobile phase. The critical parameters of an ideal mobile phase in SFC should be easily achievable using available instrumentation capabilities. It should have the following desirable properties. 1. High solvent strength. 2. High diffusion. 3. Inertness. 4. Compatibility with detectors. Carbon dioxide is the most common choice as mobile phase in supercritical fluid chromatography. This is because carbon dioxide has mild critical temperature and mild critical pressures. It can reach high densities around 40 degrees at pressures less than 40 MPa. It is inert, non-toxic and non-corrosive. It is compatible with various detectors and has wide range of densities that can be modified by changing the operating conditions. There are many other supercritical fluid chromatography solvents as choices other than carbon dioxide. For example, nitrous oxide or N2O. It has got similar solvating and separation properties as carbon dioxide. Alkanes such as butane and pentane, they can also be employed. However, they suffer from a disadvantage that they are less safe than carbon dioxide. They may be incompatible with the detectors. However, they possess better solvation power for non-polar solutes. Halocarbons, xenon, etc. are also used for very special applications. More polar solvents are required for highly polar and high molecular weight compounds. Pure supercritical fluids as mobile phase are non-polar and polar solutes are typically insoluble in them. The highly non-polar nature of carbon dioxide is a serious disadvantage with respect to elution of polar compounds and biomolecules. Therefore, organic modifiers are added to carbon dioxide to increase the solubility of polar compounds. These are also known to deactivate the undesirable interactions between the analyte and silanol groups of the stationary phase. These are known to be responsible for non-elution of the analytes. Nowadays, supercritical fluid chromatography using pure supercritical fluid as mobile phase is rarely employed. Methanol is amongst the most commonly used polar fluid that is completely miscible with carbon dioxide and used as the modifier. Typically, SFC is operated at 0 to 40% of modifier concentration. Besides methanol, following different organic molecules are used as modifiers. For example, isopropanol, dichloromethane, tetrahydrofuran, and acetonitrile. Methanol is by far the most widely used modifier and amongst the most polar modifier that are completely miscible with carbon dioxide. The advantages of methanol include availability, cost effectiveness, complete miscibility with carbon dioxide, low UV cutoff, relatively low toxicity. The range of solutes that can be analyzed by supercritical chromatography has been extended significantly by the use of a mixture of mobile phases, that is, carbon dioxide, methanol, which is a modifier, and a low concentration of a much more polar substance called as additive. Elution of highly polar compounds such as aliphatic amines and polyfunctional acids cannot be achieved using pure carbon dioxide or binary mixtures of carbon dioxide and modifier. The inclusion of small quantities of a third substance known as additive is often required that results in efficient elution of the polar compounds. The additives are generally stronger members of same functional group as the analyte. For example, trifluoroacetic acid used for the elution of other acids, isopropylamine for eluting amines, acids or bases for elution of bases or acids. There are two different types of SFC columns. Open tubular, that is capillary columns, which are also used in GC, or packed column just as in HPLC. The open tubular columns have been derived from gas chromatography or GC columns. Most commonly, fused silica columns coated with polysiloxane stationary phases are used. The selectivity or polarity of the stationary phase in open tubular columns can be modified by functional group substitution. Alternatively, packed column can also be used. These are much more popular than OTC, that is open tubular columns, in today's world. These have been derived from HPLC. Modified silica based stationary phase are the most common stationary phase used in SFC columns. The retention times in supercritical fluid chromatography are a complex function of following different factors. 1. Operating temperature, the density or the pressure. 3. Mobile phase composition. Parameters affecting capacity in supercritical fluid chromatography. The effect of density of a pure supercritical fluid on retention at constant temperatures is simple. An increase in density is always accompanied with lower capacity factors. At constant density, however, capacity factors decrease regularly with temperatures. The effect of temperature on retention at constant pressure is much more complicated. Depending on the operating pressure and temperature, a temperature increase can either lead to an increase or decrease in capacity factors in supercritical fluid chromatography. Effect of modifiers. Retention in supercritical fluid chromatography is governed by the combination of properties of both the mobile and the stationary phase in relation to that of the solute. The addition of a modifier to the mobile phase can induce changes in the nature of either of these phases. Hence, the effect of adding a modifier can be divided in a mobile phase modification effect and a stationary phase modification effect. The observation that small amounts of modifiers have large influence on retention and peak shape in packed column supercritical fluid chromatography. It is generally assumed that residual silanol groups on the surface of packing material are responsible for poor peak shapes and excessive retention times often observed for polar solutes in packed column supercritical fluid chromatography. If active silanol sites are not properly deactivated, adsorption at these sites contributes to a mixed retention mechanism. Addition of modifiers decreases these types of interactions. Modifier effect on stationary phase. The packed columns for supercritical fluid chromatography are chemically bonded phases that have originally been developed for liquid chromatography. They are prepared by the reaction of silinating agents with hydroxyl group on the surface of small size silica particles. This reaction has been known to be never more than 50% complete. Therefore, there are free silanol groups on the packing material. Subsequently, end capping reactions are carried out by which the residual silanols are removed. A considerable fraction of silanol still remain free. The free silanol groups result in retention of solute. This causes increase in retention times and poor shapes of chromatographic peaks. When modifiers are added to the mobile phase, they get adsorbed on the silanol groups. If this interaction is stronger than that of solutes, the effects of silanol groups are suppressed. To summarize, in this module, we have introduced the technique of supercritical fluid chromatography. Supercritical fluid chromatography offers numerous unique features which can be employed for analysis of a broad range of molecules. Supercritical fluids have properties that are intermediate between gases and liquids. The advantages of supercritical fluid chromatography includes fast and efficient analysis, a wide choice of detectors, low cost, and eco-friendly mobile phase. Carbon dioxide has been the solvent of choice for carrying out supercritical fluid chromatography. Open tubular columns or packed silica-based columns can be used for supercritical fluid chromatography. Though analysis of polar compounds is difficult with pure carbon dioxide as mobile phase, modifiers and additives can be added, which affords the analysis of polar molecules also with SFC. Thank you.